this video, we'll be proving this theorem. We'll show that a matrix is diagonalizable if and only if it has a basis of eigenvectors. So I need n linearly independent eigenvectors where n is the size of a matrix. Alright, so we're going to prove this. Since I have an if and only if, I have to prove two directions. I have to prove that if A is diagonalizable, then this statement is true. And I have to prove that if A has n linearly independent eigenvectors, then A is diagonalizable. So I'll start with the first implication. So I'm going to assume A is diagonalizable. So that means I can find a matrix P. And a matrix D. Sorry, there are matrices P and D, so that P A P inverse equals D, and D is diagonal. Perfect. So I'm going to take P to be made up of column vectors. Those column vectors will be P1, P2, and Pn. So what I want to prove is that these vectors are the ones I'm looking for. So they're eigenvectors and they're linearly independent. Alright, so let's prove both. First thing I want to say is that they're eigenvectors. Alright, so I'm going to use this identity here. I'm going to send P inverse to the other side. So if D equals P inverse AP, that means that PD equals AP. Now I want to use this to show what happens when you apply A to PI. Right? So if I take AP and multiply this by EI, by this I mean the matrix that has an I, a 1 in the ith spot. Then I'm going to get, if I multiply this by PI, I'm going to get, by EI, I'm going to get just PI. Alright, so A acts on PI, I can use AP on EI. But now AP is the same as PD, so if I apply PD on PD on EI, well, PD and AP are the same, so I should get exactly the same thing. So let's see what that gives us. So this 1D is a diagonal matrix. If I multiply that diagonal matrix by EI, then this is in the ith spot, it's going to catch DI. So it's going to catch DI, I'll be left with P1, PI, Pn, and then the new vector here will be the same, except that I'll have DII instead of 1. That's still in the ith spot. And so if I multiply them, I get DII-PI. All right, but those two need to be the same because the matrices that I'm applying are the same. So that means that API is DII-PI. That's exactly the definition of an eigenvector. In fact, the DII would be the eigenvalue. With eigenvalue DII. Perfect. So that's the first claim we had, that the columns of the P matrix would be eigenvectors for A. The second is that they would be linearly independent. That one's not as lengthy as this. So I want to prove that this is linearly independent as a set, but if you remember, P was the matrix with these vectors as columns. And so if I want to test whether this is linearly independent or not, what I should do is reduce this matrix. And I want to make sure that I get a leading one in each of the columns. That way, the vectors are linearly independent. But what we're told is that this matrix is invertible because I have P inverse everywhere. So if this is invertible, and so that means when I reduce, I get 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, and so on. I get IN, and so yes, P1, Pn is linearly independent. All right, so that's one direction. That proves that if A is diagonalizable, then I need to have n linearly independent eigenvectors for that matrix. Now we need to prove the converse. I need to prove that having these n linearly independent eigenvectors, that's enough. So I'm going to assume that I have n linearly independent eigenvectors. Let's say I know what their eigenvalues are. The eigenvalues are lambda 1 through lambda n. Alright, so now what I'm going to do is I'm going to take p, like we've learned, I'm going to take p to be those vectors as column vectors. Now, just like we saw here, because they're linearly independent, we would have an invertible matrix. And so all I need to check now is that P inverse AP would be a diagonal matrix. So let's check. All right, so let's see what we get. If I take AP, that's A times P1, P2, Pn. So if I multiply it, I'll get A times P1 as the first, A times P2, and A times Pn. So that's going to be, well, those are eigenvectors, so it's lambda 1, P1, lambda n, Pn. Right, so now is the time I want to introduce a diagonal matrix. This is the same as P1, P2, Pn times a diagonal matrix with these lambdas on a diagonal. Lambda 1, lambda 2 would multiply P2, lambda n would multiply Pn. Alright, so I get P times D. Notice that what's cool here is I managed to transform AP into P times D. And so now if I put the P minus on the left, I'll get P minus AP is equal to P minus PD, which is just D.